This is a What the Physics video on uniform circular motion. Specifically, oh yes, everyone's laughing. You don't have to suck up. Oh, that's so great, Fair. Oh yes, wonderful. Okay. It's going to be focusing on different types of motion, specifically different types of velocity, yes? Okay, so types of motion. So far, what we've been discussing is just going from point A to point B. Fancy word for that is translational. Okay, so I'm in a car, I start up here. That's not me, but okay. But look at this. Yeah, see? Look at that. Do it again. Okay, last time. Okay. Yeah, it took hours. Okay, so like we said, that is translational motion. Not necessarily a straight line because we actually have done some curvy stuff with projectile motion, but even that was a parabola. Now what we're going to be doing is talking about motion from point A to point A. You say, what? What does that mean? Well, perhaps this wandering monk or whatever he is can help us with that. Begin. Walk, 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 walk. Zoom, 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 zoom. Dabba, 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 dabba. No, it is not me. Okay. So it's not a perfect circle. Yeah, I recognize that. But we're pretending it's circular motion, right? Okay. Oh, this symbol here. It's like, oh, that's the recycling symbol, right? No, not quite. But it is, as far as I'm concerned, pretty good for circular motion, right? Because the arrow's implying motion, yeah? In a circle. Ah! Okay. All right, folks. Okay. So, what is circular motion? And because I figured someone, is motion in a circle? Well, yeah, that's what I said here. Okay. But it doesn't have to be a full circle. And by that we mean it can just be part of a circle. So if I'm going around a curve, technically that is circular motion. I do not have to do a full circle to do circular motion. If I'm driving a car and I'm going up over a hill, if I can simplify the rounded top of the hill into at least kind of like a circle, yeah, that's circular motion. If I'm driving down the hill and there's another hill ahead of me, so the kind of the trough part, like the valley, if you'd like, okay, that would also be circular motion, at least for a little bit, right? Okay, going around curves, circular motion. Sure. Give me some other examples of circular motion, please. Oh, I'm not going to call names, so I'm just going to have to point. That way you don't have to be embarrassed, like, oh, he said my name. No. What's that? A Mias wheel? What's that? A Mias wheel? Ferris wheel! Okay, no. All right, okay, yeah, Ferris wheel, a merry-go-round, okay. A lot of amusement park rides. What else? A bicycle wheel, okay. If we're talking about any particular point on the bicycle wheel going around and around, sure. Yes? An old record, okay. If I say record player, do you guys know what I'm talking about?
You put the pin. Like you record and it plays it.
Yes. Yeah. I've never had a record play. Okay, so you said record notes and it'll play it for you. Well, I've never actually seen one that would record for me. I think that's a gramophone or something like that. But anyhow, yeah, a record and record players. I mean, they still exist, but I don't know if you've ever seen them before. But anyhow, yeah, it's like an iPod that spins around. Yes, okay. Anyhow, it is an example because the record is spinning around. Okay? Good. What else? A circle. Well, is it doing anything?
How about a car? A UFO.
A circle just by itself is not doing anything. If we're talking about a circular shaped object moving, then yeah. Yes.
A circle that's on a circular track.
A circle on
wheel.
a circular
Going
track.
around a circular track.
A circular wheel, as opposed to the non-circular wheels that are on tracks. But yes, a circular wheel going around the track. Okay, yes.
Does a 360 don't count?
The solar system. So, for example, Earth going around the sun. Not a perfect circle, but as far as we're concerned, it's pretty awesome. Yes.
Flying saucer.
A flying saucer. What do you mean? How is that circular motion? Okay. So at least the way we often visualize a flying saucer is it's spinning around, right? We'd see like a particular point on the saucer spinning, right? Okay. Oh my gosh, really? How many more volunteers? All right, no more. No one else. No, you put your hand down and you put your.
It's a question. It's not a thing. It's a legit question.
All right. Yes.
Ice skater spinning around.
Ice skater spinning around. Thank you. Good. Yes.
360 dunk.
A 360 dunk. Oh, you saw me the other day, right? No. Okay. Hold on a second. Last example. Go ahead. A yo-yo. Yes, indeed. Sure. Question.
If you have a circle, or if you have like a saucer, and it's like a hovercraft, and it's like going like that, but it's not moving. Is that circular motion? Like
Okay, let me repeat. So, because no one could see what my student just was gesturing, let me repeat it. Okay. So he's asking about a flying saucer, and that's spinning in place, but it's not actually moving anywhere. Well, sure, yeah, that's still. What we'd say is it's clearly spinning, it's rotating. If we were to talk about a particular spot on that saucer, we'd say, okay, that spot is going around in a nice circular path. Sure, that's circular motion. That's usually what we're going to be talking about, right? We're going to be talking about if something is spinning, we'll talk about a point on that object that's spinning. Okay, good. All right, so other ones that I had come up with, we already said the Mias wheel. Driving around a curve, going over a hill, even kicking a ball. You say, how is kicking a ball circular motion? Is that because the ball is a circle shape? Not necessarily. I mean, the ball probably is a circle shape, but this thing here, as you're pulling back and swinging your leg forward, I mean, you probably don't swing it all the way from here up to there, or else, well, maybe you can do that once. Okay. I did that once. Okay, with your voice a lot higher now, of course. Anyhow, that was a joke. Okay. You use it. You can see clearly that that's at least part of a circle, right? Okay. Lovely, delicious. What's that? Is shooting a basketball. Well, if you're putting some spin on it, then yeah, there's some circular motion to it. The basketball's motion going from point A to point B would be following a parabolic path. That would still fall under the translational, though. Okay? Okay? Now, I'm not saying that we can't have both. I'm not saying that it's one or the other. If you have, who was it that said a round wheel going along, let's say, the desk here, okay? It's going from point A to point B, right? So that's translational motion. But it's also rotating, okay? The object itself is spinning, okay? So it's got rotational motion too. And as we'll see, we can look at it and we can try to calculate the tangential velocity from it too. Like, ooh, what are these amazing words? It's so exciting. So, when we were talking about linear speed, we were talking about distance divided by time. Okay? And we did pretty well with that in one dimension. If we're talking about an object that is spinning around, we say like the flying saucer, Let's say there's a door on the flying saucer. As you see the door spinning around. Or if you're talking about the Earth going around the sun or whatever. If you're talking about that particular point, you can calculate its tangential velocity. Tangential referring to a tangent line. Now, you've certainly heard of tangent in terms of geometry and, in pre-calc or calc or I don't know when it is you guys specifically talk about tangent lines. But a tangent line, not in terms of a triangle, but in terms of a circle. What does a tangent line do? It hits the curve at one point. Right, just touches it once. Okay? And, someone was saying something about perpendicular. Go ahead. No names, please. Guy, yes, okay. You. All right. The tangent line is perpendicular to the point. Well, okay. I don't know if you can really be perpendicular to a point, but if you were to make a circle out of that curve, then it would be perpendicular to the radius of the circle. How about that? Okay. Or you could say there's just as much space between the tangent line and the curve on, say, the left side as on the right side. Okay. Good. All right. So we're talking about tangential speed or tangential velocity. We just call it v here, and we'll see why in a little bit. If we have a wheel here and it's going from one place to another, if we pay attention to the object's center of mass, then it does a translational motion. That's shown in the blue, right? It's going from here across here. It doesn't actually move here. Don't worry. Okay? The red arrows are the tangential velocities. As in, hey, how about this little spot right here? How fast is that going? Okay? Well, it's going around in a nice circular path, so it's the circumference divided by the time. Okay? A rolling object can have translational and tangential speeds. We do have to carefully distinguish those. When we're also about to talk about rotational speed, we'll have to distinguish that as well. Okay? So it should be obvious when we look at things. Hey, does it rotate? Does it have tangential? What does it have? This ceiling fan, does it have translational? Does it have tangential? Does it have both? Does it have neither? What do we think?
It has tangential speed.
The ceiling fan has both tangential and translational?
It does not have translational.
It does not have translational. Yeah. Unless you've got some ceiling fan of doom that is chasing you around the room, that would not be a good situation. Yes. Okay. Science fit. No, we don't want that. Okay.
We call an object with no translational motion a rigid object, or something like that. Like a rigidly placed object. Because it's in the textbook.
Okay. I'm sorry. Say it again. Call an object that is
Doesn't have translational speed. It would be just a rigid object or something.
Okay. No, a rigid object is referring to. We'll see that on the next slide. Okay. Hold on to that question. Okay. It just means it's all kind of. The shape isn't changing. It's all moving together. Okay. So. How about this? Okay. This image right here, is that going to have tangential? Is it going to have translational? What do you think? Why? Why do you say that? Well, okay, physically moving is not adequate. What do you mean? Okay, he's moving from point A to point B. So, all right, now, I was very general when I asked the question because you could answer this several different ways. I mean, it's clear implication that he's moving, as in from point A to point B. So that would be what type again? Translational, yes. Is there also going to be tangential? Okay, well, it depends on what you're referring to. If you're just referring to the dude in the wheelchair, no. If you're referring to the wheels on the wheelchair, yes. Yes. Okay? How about this one? What do we think? Once again, vague question. What do we think? Oh, it depends. I know, but you got to make a choice and support it.
Translational.
All right, hold on a second. Raise up your hand. I'm not going to call on your name. Yes. You, Uber.
Translational because it's moving from point A.
All right, so translational, it is moving from point A to point B. Does it also have tangential?
Yes.
It depends.
Okay. It depends, once again, what you're talking about. Or you could argue, I mean, I could argue that, no, it doesn't have either of those. Because to me, it looks like it's parked, right?
Yeah.
Okay, sure. Okay. Yes, it is a still image. Thank you very much. Harry Potter did not come along and try to animate this object. Okay. I just thought this was kind of funny because it looks like some type of Hummer, and then with wagon wheels, so that was amusing to me. But yeah, if we're talking about the wheels, they can have tangential and translation. Okay, so more about speed. We've talked about tangential and translational. Now let's get rotational in there. Woohoo! Too many speeds. Right. Okay. Rotational speed is the number of rotations of an object divided by the time. That means how fast the whole object spins. Okay, so if it's a tire, if it's a merry-go-round, if it's a flying saucer, like we mentioned, what else? If it's a pizza, sure. Okay, but in this case, we're not talking about speed in terms of like meters per second. Okay, we're talking about rotations per second, or per minute, or whatever. Okay, or we can even do partial rotations. Your textbook, I believe, it was starting to talk about angular motion, and we can talk in terms of like degrees per second, or if you want to do annoying radians per second. Okay? All right, but anyhow, okay, for this, we've got to look at how the object is moving. So first of all, this is when we talk about it being a rigid object, okay? So the object is not changing shape. We're not saying this part spins at one rate and this part spins at another rate. So this disk is a solid disk, okay? There aren't like rings that go at different rates, okay? So if point A, let's say that takes 10 seconds to go all the way around, how long will it take point B to go all the way around? 10 seconds. And how about C? Okay, and the reason it takes the same amount of time, 10 seconds for each, is because it's a rigid object. It's a solid object. Everything is rotating, or that object is rotating, and those points are revolving if you want to get really picky. They're all going around at the same rate. Okay, so the angle is swept out the same for each of those. If I were to talk about tangential velocity, would they all be the same? No, and why not? Say it loud, please. Because the radius is increasing, or in general, radius is changing. So if I were to look at this guy's circle, or its circumference, it would be relatively small to this guy's, right? And certainly small relative to this guy. Okay? Now, if they all travel around in the same time, but the circumference is larger for point C, what can I say about tangential velocity for point C?
It's greater.
It's the greatest of all, right? Yes, good. So, I've already kind of mentioned circumference because it's going around in a circle. Okay, we're actually going to calculate it using this equation, circumference divided by T. That's a capital T, that means period. Okay, period, capital T, is a specific time. It says, how long does it take for something to occur? How long does it take for this disk to spin around? We said 10 seconds, right? How long does it take for the Earth to go around the sun? Well, that's 1 year. or 12 months, or 365 days, or 52 weeks, or 525,600 minutes. Right, okay. Yes, okay. Now, that's period. It's how long something takes to occur. That is the inverse of frequency. If I'm talking about frequency, I'm talking about how many occurrences per time. This occurs 5 times in 1 second. Or you have to come up here, you come to this classroom so many times a week, right? That's a frequency. Yes. Yes. The question was about like how many rotations per minute, per second, whatever. RPMs, RPS. If those folks that have actually looked at the record players, in museums before, you would have seen like, oh, 45s, or what's the 45 referring to? Okay. Well, yeah, it's RPMs. Yeah. Okay. Okay. Yes.
Frequency measured in hertz.
A frequency can be measured in hertz. Doesn't have to be, but that's kind of our standard. Hertz implies one occurrence, well, some number of occurrences per 1 second, I guess I should say. So if I said this goes around 5 times in 1 second, I'd say the frequency is 5 hertz. Okay. If I have something in hours, I could convert that into like 12 times in an hour. I'd have to say, oh, let me convert that into how many times per second, and then that would be the frequency in hertz. Okay? So, frequency and period are related. It's once you got one, it's really easy to get the other. But let's make sure we understand the difference between them. Okay? If I were to clap at 1 clap per second, and I'm not like very good at rhythm or anything, but yeah, 1 CPS, wonderful. I'm not necessarily saying I've got good rhythm here, but let's say, okay, this is about 1 clap per second. Oh, great! I've got backup clappers. Okay, 1 clap per second. That's a frequency. Okay, that's enough. 1 clap per second is a frequency. If I said, how long does that clap take? You'd say, oh, it takes 1 second. That's a period. You say, oh, frequency and the period are the same, right? No! Okay. How about if I were to try to clap twice per second? Okay. Something like this is twice per second. Oh, someone has no rhythm, and that could easily be me. Okay. Well, all right. Wait. There's a bunch of band people or music people in here. Who's gonna volunteer to drop a fat beat for us? Not names. Just raise up your hands, please. Okay. Do you want to do it? Can you? Okay. So let's do 2 beats per second, 2 claps per second, please. What is no? Oh my gosh! All right, not you. Okay. Can you please try it? Yes. Out loud. Okay, good. Now I'm going to need you up here so we can hear you, though. Okay. All right. Okay. So that was what? That was
18 beats per second. 120 beats per minute.
120 beats per minute, which would be
120 clicks in the biz.
Oh, oh my gosh! I should not have asked for anyone to help. So what would the frequency be in hertz? 2 claps per second, or 2 hertz, right? So how long did it take him to clap just once?
Half a second.
Half a second. That's the period. So as we can see, if you could do it 3 claps per second, I don't know if you... All right, go ahead.
I got it.
Okay. Yay, physics! Yay! All right. So 3 claps per second. Okay. 3 claps per second. And what we see there, how long would it take to clap just once? A third of a second. So period and frequency are related how? One goes up, the other one goes down, right? They're inverses to each other. So if I have the period, all I have to do to get the frequency is say 1 divided by that, right? If I have the frequency, all I have to do is say, oh, I want period. Oh, 1 divided by that, right? Easy, easy, easy. So as soon as you got one, you've effectively got the other. The biggest challenge is making sure you know which one you've got. Because if you misread it, you say, oh, this is the frequency on any period. No, it might already be the period. Who knows? Okay? That just comes from reading and interpreting. If it says this happens so many times per second, that would be a frequency. If it says it takes this many seconds to occur, that would be a period. They're not always quite that obvious, but, reading and interpreting. Anyhow, so that means I could actually rewrite this equation as velocity is 2 pi r f. And by the f, I mean little f. We use little f for frequency. Not big F. Big F would be for force.
Wait, why is... I don't get it. I mean, like...
What is wrong, sir?
I mean, why would they make it little f?
Why would they make it little f? Because f is the first letter of frequency, and we don't want to use big F for force, right? Or because we're already using it for force, yeah?
Does that say F?
Okay, let's keep going. Good, good? Delicious. All right, speed example. So, Martin's riding his bike. It's spinning at 90 ripums. That's rotations per minute. The bike is a meter tall. Calculate the rotational speed in rotations per second. Tangential speed of a particular spot on the outer edge. Tangential speed at a spot halfway between the axle and the tire. And then the rotational speed at that same point. Goal. Okay, so let's see what we can do here. So we already read it. We can list out the information and such. What do we have in terms of information, please? Rotations per minute is what?
90.
Okay, but what does that mean? RPMs is a what? It's a frequency, yes. Okay, so the frequency is 90 RPMs, rotations per minute. So if I put it like per minute, and I want to convert into seconds, this is easy, or rotations per second. That's just a simple conversion. What are we going to do?
60 seconds, 1 minute.
90.
Okay.
Well, you can use dimensional analysis.
Yes. 1 minute is 60 seconds. Where am I going to put minutes? On top or on the bottom? Top.
Train tracks.
Or like we did earlier this year, but sure, yes. Yes. Okay. So, we're now left with rotations per second. What's that going to be?
1.5.
Rotations per second.
RPS. Yeah.
1.5 rotations per second. Now, I think people were trying to get the period when they were saying kind of the wrong information. If I want to get the period, what would I get? Okay, which is what? If you like to use your calculator, go ahead. Folks, if 1.5 is the last thing in your calculator, what can you do to easily get this calculation? Just say the x to the minus 1 button, enter. There we go. What is it? Say again. 0.6 repeating. Seconds. And that's seconds per rotation, but you can just say seconds. Okay? If you want to say 0.67 or 0.667 or whatever, I don't care. Okay? But that's not the answer. The question was the tangential speed at the spot on the outer edge. You can use either one of those equations. Either one of those would be just fine. Okay? To make sure that we understand what we're talking about, though, this is 1 meter. So we want to use 1 meter? No. Okay, so 0.5 meters. Wrong. 2 times 0.5 is 1, and then times pi, yeah? Okay, and then either multiply by 1.5 or divide by 0.6. Repeating, yes. What do we get? Same either way. What should you get? 4.7 or 4.71 meters per second. Wrong.
Attention, Senator, we do have a couple of passages.
So we have the tangential speed at the outermost edge, that would be like right there, as 4.71 meters per second. Now if we're talking about the tangential speed at a spot halfway between the axle and the tire, so right about there, let me go ahead and mark that. We can use the exact same equation and the exact same information as before, except our radius is going to be smaller. Instead of half a meter, the radius is going to be 0.25 meters. Okay? We tap that into our calculator, and we get 2.36 meters per second. 2.36 meters per second. In the case of D, in the case of D, the rotational speed at a spot halfway between the axle and the tire, well, how would that change at all from part A? It doesn't. The rotational speed is the same throughout the whole thing. It doesn't matter where it is in terms of distance from the center. Also worth noting here is what it says. Notice that when radial distance is doubled, tangential speed is, well, that's going to be doubled. Okay, the tangential speed, as we said, is based upon how far out we are. Assuming the rotational speed is constant, then if we double the radius, then we're going to double the tangential speed, because the period and frequency, those are fixed values. So let's see. There's that. Okay, and then the last questions or set of questions was the speed conceptual questions. Okay, so these are just focusing on the concepts, not so much the calculation-y types. I mean, a little bit of calculation. So Thayer uses his physics to spin a basketball on his finger, demonstrating circular motion, and his wishful thinking, seeing as he lacks all basketball skills. What part of the ball has the largest rotational speed, and which part has the largest tangential speed? When I'm talking about the ball, this is kind of an overhead view. Oh, goodness gracious, that's the wrong thing. Let's see if I can do that again. This is a kind of overhead view of the ball. Okay, it doesn't look like much of a ball, but that's okay. We just imagine this is an overhead view of the ball. Rotational speed is not going to vary at all. Rotational speed is the same throughout. But when we say the tangential speed, that is going to be, actually, let's not make this an overhead view. Let's make, say this is the axis of rotation. And here is a very small sized fair for some reason. And it's spinning around on the fingertip. Okay, so it's going around like this. Okay, they all have the same rotational speed, all those points on there. The tangential speed is going to be largest where? It's going to be largest right out here at effectively the equator spot. The tangential speed is going to be largest when it's farthest away from the axis of rotation. Okay? Now we've got fair jumping rope. So if fair tries to jump rope, trying to figure out the maximum, or the optimal time to jump. He estimates the speed of the rope by his feet is 2.6 meters per second. How fast, that is the tangential speed, is the rope going halfway between that point and his hands? Let's see. Okay, so there's the jump rope in green, and we're talking about the farthest point away as 2.6 meters per second. If we're talking about halfway up, what's going to be different? .6 meters per second. Well, what would it be right here? Well, right there, it's going to be half the radius. Now, you never gave me a radius value, fair. That's okay. I just know the radius was cut in half. So what is going to happen to the tangential speed? It is also going to be cut in half. Okay, easy enough to figure out what half of 2.6 is. That's going to be 1.3 meters per second. And if we're talking about something that's a third of the way from the axis of rotation for my hands, well, maybe down here, I guess. Okay. So we just say, what is 1/3 of 2.6 going to be? That's going to be 0.867 meters per second. 0.867 meters per second. We used the concept that we had figured out last time. Let's see. This guy right here, when we double the radial distance, we double the tangential speed. So that's how we were able to figure out those values even without any calculations. So tangential speed is proportional to radial distance times the rotational speed. Physics. You gotta love it.